In this video, we're going to introduce the concept of area. And we already have an intuition from geometry about what it means to find the area of a certain shape. For instance, if we have a rectangle with dimensions height A and base B, then the area of the rectangle is defined as A times B. And we have a similar kind of formula if we have a right triangle whose height is A and whose base is B, and the area of this triangle is defined to be 1/2 A times B. Now, if we have a polygon with straight sides, then the area can be found using a couple of different approaches. We could divide this polygon up into 4 triangles, and each triangle has an area. We'll call it area 1, area 2, area 3, and area 4. And the total area of this polygon could be found by just adding each of the 4 areas. Area 1 plus area 2 plus area 3 plus area 4. And each of those triangles can be found using the 1/2 base times height idea. For instance, if we drew a thinner line here, if we drew a line perpendicular to the base of area 2, let's say area of triangle 2, would be found by creating an altitude that is perpendicular to the base. So the height would be A here, for instance. This would be our A. And our base would be along that edge. And area 2 would be 1/2 A times B, where A is this height perpendicular to this base. Now, it might involve some trigonometry or geometry to find it. It's not necessarily easy, but it can be done. And the point here is that we have a formula to find the area of triangles using the formula 1/2 base times height. Now, in calculus, we can find ourselves needing to find areas of regions enclosed by curved edges or boundaries, not just straight lines like we had above. And in this case, we would want to find the area, say, under the curve y equals f of x, this curve here, from x equals a to x equals b. So you can see this is an enclosed region here, and we want to find the area under this curve. And so there are a couple of different strategies. I'm going to introduce one in particular that uses rectangles, and then we might discuss some other approximation methods in later videos. So one strategy here, one of the more basic strategies to find the area under a curve, is to divide this area, or we can consider the interval from A to B. We're going to divide that into, let's start off with just dividing it into 2 equal, well, when I say equal, I'm considering this interval from A to B. I'm going to divide the interval AB into 2 equal parts, roughly. I'll do my best. So here, I've divided AB, the interval AB, in half. And so what I can do then is I will draw a rectangle by connecting the right endpoint of this half over here. I'm going to go straight up here, and I'm going to make a rectangle off of that. And then I'm also going to make a rectangle off the right side of this. So now I've got basically 2 rectangles, and I can find the area of these rectangles if this is the base. We'll call that a little change in x. And this is another base. And it's going to be the same because I've divided the interval into easy parts. We'll call delta x. I'm calling it delta x just because it's a small change in x along the x-axis. You could call this anything you wanted. You could call this base if you want. I wouldn't call it little b because we have a b there, but you can call it base there if you want. That's fine. Now, the height here, call it h1, isn't necessarily, it turned out that it's the same here, but that's a coincidence. We'll call them height 1 and height 2 and pretend we don't realize that they're the same in this special case. Now the height is actually a specific value. Here we have b, that's our x value. The height is simply f of b. That's because at x equals b, the height goes up to the curve. Anything on the curve is you just plug in the x value and you get the y value. Plug in b for x, f of b, and that's your y, or your height. Over here, if this was, say, x1, then this height is f of x1. Now I'm making up x values as I go along. These will actually be numbers. In the next video, I'll give an example with specific numbers. Okay, now, let's say we wanted to divide this interval instead of into 2 equal parts. Let's say I want to divide it into 4 equal parts. Let's see how that looks. So now I've got 2. Let's divide this further. Now I'm going to divide the strips into 4 equal parts. Okay, now I've divided the region into 4 strips with equal width. And let's be a little bit more specific now about what I'm letting each value be. So here's a, we'll call a x sub 0. And this will be x sub 1. And this will be x sub 2. And this will be x sub 3. And this will be x sub 4. And that's b. So b is x sub 4, a is x sub 0, and then we're going along. This just helps us with understanding notation, because in my first example with 2 strips, I didn't use this, and it actually will be easier to keep track of things as we go along. Make this yellow. Looks like it's red. All right, now I want to make rectangles off of the right endpoint, or the right side of the strip. So I'm going to bring this over, and there's my height. So I'm making height off the right endpoint. So now I have 4 rectangles, and each rectangle has the same basic base, the same base value, and we'll call that base, let's change colors here. We're going to call each of these bases a change in x. They're all the same. And there's a way to find delta x. We'll go over that in just a moment. But here, now the heights of each rectangle, the x value is x1 here, the height going up to the curve. Anything on the curve, you just plug in the x value, and you get the y value. The y value gives you the height of the rectangle. So in this case, the height is f of x1. The height at this point, if I plug in x2, the height is f of x2. The height of this rectangle is going to be f of x3, and the height of this rectangle is f of x4. So if we want to find a rough approximation of the area under the curve from A to B, so this area over here, divided into strips, and in this case, just for presentation purposes, I've divided it into 4 equal widths, 4 rectangles. of equal width. Okay. And now the area, if I call this area 1, area 2, area 3, and area 4, the area under the curve is approximately equal to area 1 plus area 2 plus area 3 plus area 4. Now, area 1 is the base times the height. The base is delta x, and the height is f of x1, plus the base of area 2. The base of the rectangle with area 2 is delta x, times the height is f of x2, plus the base of the rectangle with area 3 is delta x again, times the height is f of x3. And then the final rectangle in this case is base is delta x, and the height is f of x4. So we can factor out a delta x. There's a delta x in each of these factors. So I can factor out a delta x, and then multiply times f of x1 plus f of x2 plus f of x3 plus f of x4. Now, a couple of comments before we finish up. One is, this is an approximation using rectangles whose heights are determined by the right endpoints of these little subintervals. We could have just as easily used the left endpoints and created rectangles off the left endpoint. And that has a very similar logic, same basic idea as we demonstrated here. Another is, we only gave examples that illustrated 2 and then 4 rectangles. You could do this for as many rectangles as you like, and the whole idea is the more rectangles you use, hopefully the better your approximation becomes. For instance, if I were to use, instead of just, if I were to use, let's say I start off with 4 strips of equal width, and then I cut each of those strips in half, making that 8 strips. So the rectangles get thinner. And then let's say I wanted to go with 16 strips, so each of those got cut in half. Then what ends up happening is these rectangles get thinner and thinner, but the approximations get better and better. So you can notice the error between the curve and the rectangle is smaller here than it is with just 4 rectangles. That's the idea, is in general, what we hope to build is a set that, as the number of rectangles approaches infinity, then the A1 plus A2 plus AN, so all these areas become very, very, very thin strips. That approaches our area, our precise area, A. So in other words, as the rectangles get really, really thin, or the number of rectangles increases, so we have basically infinitely thin rectangles or strips, then adding up all these individual areas, area 1 plus area 2 plus area 3 and so on, these end up getting much, much closer, and they approach the area A that we're shooting for, which is the area under the curve. So that's the basic idea of how you find area under a curve in calculus using rectangles, in this case rectangles with right endpoints. In the next video, I'll go over a specific example with a particular equation or formula for y equals f of x and fixed numbers for a and b. I hope this helps.